In the last few videos, we were discussing the very important problem of constructing a linear model from a practical description of the problem. That is very important, and we have not yet finished discussing that. But now we shall pause that topic for some time and take up another topic which will be closer to what our textbook presents, and which will also justify the use of the term statistical in linear statistical model. So when we talk about a statistical model, we naturally expect that we make some specification of some random quantity. Now in our model, that random quantity is epsilon, the errors. Of course, the measurement y also are random, but they are random because epsilons are random. So the epsilons, the errors, are the root causes for which we get randomness in the entire scenario. So that x beta part is usually called the structural part, something that is fixed. Part of it is known, the x, part of it is unknown, beta, but it is fixed, so that is the structural part. And then we have the random part, epsilons. These two things together combine to produce the measurement y, which is also random. So the root cause of randomness is the epsilon. We need to put certain assumption on epsilons. That's why it will be a linear statistical model. Now we can put certain assumptions directly, say that let's assume epsilon satisfy this condition, but instead of doing that, we shall try to come up with a set of conditions which are natural. That is, instead of imposing some conditions from outside, we want to see what are the natural conditions that from just intuition or common sense we feel that epsilons must satisfy. Suppose that we want to measure the length of this bar. Now, we know this is a very standard problem in physics, in many other branches of science, where we have to take some physical measurement. So suppose I take this scale and try to measure this length, and it turns out to be something. So we get one particular measurement, and that, according to our model, we can write it as y1 equal to beta plus epsilon 1. So beta is this length, the true length, and y1 is the thing that I got by measuring it, and epsilon 1 is the inevitable error. Okay, so I will take a number of measurements. That is the standard practice. I will measure it again, I will measure it again, and every time I will take the measurement of the same thing. Had there been no error, I would always get the same number, but because of some random fluctuations, I will get some slightly differing things, and as a result, I will get a system of equations. So y1 equal to beta plus epsilon 1, yn equal to beta plus epsilon n, yn equal to beta plus epsilon n. So that is a linear model. Now let us see how we shall get the least square estimator based on this. So if I write it as a least square model, a linear model, in that case I get this scenario. I have y1 to yn, then the design matrix is x1, 1, 1, 1, 1, 1, unknown beta vector is in this case just a single scalar beta, and the epsilon 1s. So what will be our normal system of equation? That is pretty easily seen. It will be that x prime x transpose x, beta equal to x transpose y, which in our case will turn out to be x being just this vector of all 1s. So x transpose is nothing but all these 1s lying horizontally. Then this is x, so that is x transpose x, and what is followed by this beta. So x transpose x beta is nothing but 1, 1, 1, 1, then 1, 1, 1 beta, and then again x transpose is another 1, 1, 1, 1, 1, and y 1, 1. So what is this? It is pretty simple in this case to work out. So all the 1s put together that will give rise to all 1 1 1 1 1 1, that will be 1 times 1 1 times 1, so it will give you just n times beta hat equal to, similarly all these 1s 1 and y1 will give you summation yi. So it will be beta hat equal to y bar, summation yi divided by n, total number of observations, that will be simply y bar. And you know that is a very natural thing to do, right? Even without thinking about least squares and linear models and all these things, if you take multiple measurements of the same quantity and you want to combine them into a single number in a meaningful way, taking the average is the very first thing that comes to our mind, and that's what we are getting, even without thinking about linear models. Now let us see why we believe intuitively that y bar is a good thing to do. Without using any complicated statistical term, we want to explain the usefulness of y bar to a layman. What are the conditions? What are the things that we are going to say? We shall see that from that we will get a tacitly assumed statistical model. Well, the first condition that comes to our mind is this, to explain to a layman why y bar is a good thing. So when I am measuring this beta using our scale y, of course we are making mistakes, so it's quite likely that we are making mistakes, but whenever we make a mistake, it could be either overshooting it or undershooting it. Now the idea is sometimes we will be overshooting it, sometimes we will be undershooting it, and on an average, this thing should cancel out. If you think that you are always overshooting it, then of course taking the average is not a good idea. For example, if you take the time shown by various people on their watches at a certain instant and take the average of that to estimate the true time, that will be a bad way of doing it, because most people will keep their watches slightly faster. I'm not talking about mobile watches because those are just exact. But generally, if you use wristwatches or the clocks at home, they're usually more of them are running faster than slower. So fast clocks are usually preferred by people than slow clocks. So there, taking simple average will not be a wise thing. Or suppose you suddenly figure out that the scale that you are using is by mistake not marked from 0 but marked from 1. In that case, in all these cases, the error will be approximately around 1. You have made at least 1 centimeter error. In that case also, you will not use simple average. So when you suggest that simple average is a good way of combining all the numbers, you are tacitly assuming that you are as much likely to overshoot as you are to undershoot. That is why if you take lots of such random measurements, average them out, they are likely to cancel each other out. That is just from our layman's viewpoint. Now, you can write this as a more statistical sounding condition by saying that epsilon i's are on an average is 0. It might overshoot, it might undershoot, but on an average they should be 0. Expected value of epsilon I is equal to 0. So when you are suggesting that let's take average, you are tacitly making that assumption. If that assumption is not valid, you will not be willing to use average. Now that's not the only assumption. Suppose I am going to measure this 10 times. Now I am a bit too lazy, I have measured it only 5 times. And then I ask my friend to take the remaining 5 measurements. Now my friend is a rather skilled engineer and he uses not just ordinary scale but a slide caliper. So he carefully opens this slide calipers and then measures this and gets some very precise measurements. So we have got 5 measurements which are taken by the ordinary scale and 5 measurements that are done by a slide caliper. So if I average my 5 and his 5, I will get most likely 2 different numbers. Now, should I just take the average of these two? That is not reasonable because this one is just an ordinary scale, so I had to do lots of eye estimation and gives me result up to closest up to a millimeter, and even then I have to do a lot of squinting of my eye. But this one is fitted with a vernier scale. It can go on up to 0.01 centimeter, that is 1/10 of a millimeter, so this is more precise. In this case, taking simple average does not look like the best thing to do. So if I have my average and my friend's average, I would rather prefer to do a weighted average where I give more weight to the measurement taken using the higher precision instrument and less weight to the measurement taken by the lower precision instrument. I am not going to discuss how you choose those weights, but the main thing is that when we are using simple average, we are making the tacit assumption that all the measurements are of the same level of precision. Statistically, that means I am assuming variance of epsilon i's are all same. I do not know what that variance is, some sigma square positive number. Of course, if sigma square is equal to 0, that means I am just in a precise measurement setup. That is not feasible in practice. So I am allowing that the sigma square is unknown, but they are all having same sigma square. This is referred to as the homoscedastic setup. Okay, that's not all. We put yet another assumption. Suppose I am using just my scale and I will be measuring all the things myself. So I know that expectation of epsilon I is 0, variance is the same, but as I said, I am lazy. So when you ask me to do this, what I do is, well, you have asked me to take 10 measurements. Okay, I will take one measurement very carefully. And then, when I see no one is looking, I will just repeat the same measurement 9 times and say, well, I measured them 10 times and these are all the things. So you see, I am not violating my assumptions because the first time I measured epsilon 1, that expectation was 0, and epsilon 2 to epsilon 9, they are also the same thing, so their expectation is also 0. Similarly, variance of epsilon 1, whatever it was, remains constant because epsilon 2 is same as epsilon 1. But will you think that taking average of these 10 numbers is really going to add to the precision? Now remember, when we take average, we have this idea that I have taken 10 measurements and average of them, so the entire thing is more precise than the original thing. But here, the average of all these so-called 10 measurements, which are all happen to be the same number, is the same number itself. But will you put any greater faith in this average number than on the first number? No, because this so-called average is not an average at all. It is just the first number itself. So our intuition that taking average of 10 numbers will give you a more reliable figure does not work in this case. So we are assuming that all these measurements is shedding some fresh light on this. So all the errors are at least uncorrelated. Epsilon i's are uncorrelated. Otherwise, taking repeated measurement is not really a good idea. For example, I know of certain students, when I was in higher secondary, I had some lab assistants or friends who were working with lab partners rather, who had this bad habit of doing back calculating at every step. So the moment they will see one measurement, they will work out by back calculation what the value was supposed to be according to physics theory, and if they have overshot it in the very next measurement, they will write down something which will undershoot it so that the average remains the same. So they are basically making all these observations correlated, negatively correlated in their case, such that the average is indeed the value that is given in the textbook. But obviously, such an experiment is meaningless because even though you have taken, say, 100 measurements, since they are correlated, they merely reflect what you believe the value should be and not what nature says the value should be. So when we are using simple average, meaningfully, we are tacitly making these 3 sets of conditions. The first is on the mean, that all the errors must have 0 mean. Secondly, they must have the same variance, unknown, that is fine, but same variance. And the last thing is that they are uncorrelated or later we will make it more stronger, they are independent, but for the time being we say that they are uncorrelated. And these are the most simple set of conditions that we can think of to make any such measurement scenario meaningful. There are situations where it will be violated, like using various instruments of multiple precision, etc. But this will be our starting point, and these are called the Gauss-Markov setup. So whenever we say we have a linear model in the Gauss-Markov setup, we mean that the epsilon satisfies this condition. So y equal to x beta plus epsilon vector, and its components satisfy these conditions. We saw that y bar, the simple mean, has some nice properties under this Gauss-Markov setup. We shall see now in the next video that least square estimators in general enjoy certain nice properties under these assumptions.